So find the Thevenin circuit. Okay, here's where I'm gonna not use the method that I introduced to you. Remember the cookbook recipe was this: find the short circuit. Sorry, find the open circuit voltage, the open circuit voltage, which gives you your V Thevenin, short circuit current, and then you take the first answer divided by the third answer. Okay, there's only a slight modification to this. What we're gonna do is we're gonna bypass step 2, okay? Because if you do step 2, you need to do another mesh current analysis, and that's gonna take you a long time. So we're gonna find our Thevenin straight away using basic formulas that we know. Okay, so bear with me. We're gonna bypass step 2. We're gonna do step 1, and we're gonna take another way to achieve our Thevenins. So first, let us do step 1, which is find our our open circuit voltage. So open circuit voltage, which is V Thevenin. So let's copy this diagram. Open circuit voltage means that I need to remove the thing, right? So the thing that I need to remove is the current source. So I need to remove this, cut this off, and find the potential difference across the place where I cut off. So let me modify this diagram, okay? Okay, just to make sure, I want to reshare my screen because I'm always panicking whether there's a technical error. Sorry. There you go. So we want to find the potential difference across where we cut the current source off. So here and here, we want to find this potential difference, which gives our V Thevenin. So what do? We just take a mesh current analysis. So do a mesh current analysis here, here, call this IA, call this IB. Now do KVL at A. So at A, let's start from this ground. We walk up here, increase in potential by 10 volts, so positive 10. Then drop in potential, so minus. The current is IA, multiplied by the resistance. Then we go to here, we drop again, so minus. The net current is IA minus IB, because IB is opposing us. And then we return back to the starting point. So just equate this to 0. This is your equation 1. KVL at B. So let us start from, say, here. We walk through R4. So there's a potential drop because it's a resistor. Current is just IB. Resistance is 300. We go through R3. Current is also IB. Resistance is 50. Then we go to R2. Potential drop. Net current upwards is IB minus IA. Then the resistance is 200. Then we return back to the starting point. So this is equation 2. Now solve 1 and 2 to get IA and IB. Okay, excuse me. So 10 minus A then we have Oh wait, I forgot to put it equals to 0 here. Equals to 0. Let me redo that, sorry. Okay, so let me check if I punch it in correctly. 10 minus a times 100 minus a minus b 200 equals 0. Minus b times 300 minus b times 50 minus y minus x minus times 200 equals 0. So what I got is this. Okay. Um, okay. We want to find thevenin, right? Look at thevenin. It's actually the potential difference across R3, correct? Let me just clean up our diagram. It's actually the potential difference across R3. See, it's attached to this terminal and this terminal of R3. So if we can find the delta V of R3, we can essentially find the thevenin. So what is the formula for delta V? It's just I times R, correct? So that means now we equate this together. So thevenin is equals to the current through R3, which is IB, and we got IB is 2 over 125. So 2 over 125. Okay, let me just do this clearly. The current through R3 multiplied by the resistance R3. So the current through R3 is IB, which is 125. Then the resistance is 50. We punch this in our calculator, we should get 0.8. So this is our VThevenin. Okay. Now we are going to find the RThevenin by bypassing the short circuit. So we will not do short circuit. You can, okay, if you're unafraid by the I don't know how to do this, you just go ahead and do the way that I do in tutorials. So what we're going to do is we're going to take the total resistance of this configuration. Using the formulas like R1, sorry, R series is equal to R1 plus R2 plus so on, and 1 over R parallel is 1 over R1 plus 1 over R2 and so on. We're going to use these formulas, okay? So bear with me. You have to know who is in series and who is in parallel. Let me... Okay. So, first things first, when you encounter circuits like this, you need to remove the effect of you need to remove the effect of sources. So whenever you see voltage source, short circuit it means replace it with a wire. Okay. If you see current sources, you need to open circuit it. So just remove it, make it a broken open wire. In this case, we don't have any current sources. Okay, so that's good. So I'm just gonna redraw this. Okay, I'm just gonna redraw this so that it's not confusing. Okay, now calm down. You must ask yourself who is in series and who is in parallel. Wait. I didn't label this correctly. So, how to identify who is in series and who is in parallel? If you check my last past year paper video, I've already explained this quite clearly. But to recap, and the shortcut analogy is this. You think of devices as two people, okay? Think of two devices as two people. So let's say this is this person, this resistor is this person, this resistor is this person. Okay, so let's call this resistor A and person A, resistor B and person B. If and what you must know is that the two hands of the people are the two terminals of the resistor. So A's hands are the two terminals of resistor A, and B's hands are the two terminals of resistor B. So if person A and person B hold together by one hand like this, you get stand up and around. Yeah. So if you observe the camera, if person A and person B hold together by one hand like this, then they are in series. Okay, now give me your other hand. If they hold hands together like this, both hands together, then they are in parallel. Okay, thank you. Okay, we'll look at the parallel sequence later. So, okay. So if you want to connect A and B in series, it'll look like this. See, this is the terminal of B. This is the terminal of A. See, they're connected only at one hand, only at one terminal. So if you want to draw this analogously, for the people, they will only hold by one hand together. See, this is the hand of A, and then these are the hand of B. See, they're only holding together at one hand. Whereas for parallel, okay, so for parallel, we have this and this. This is resistor A, resistor B, and then we have here, so these are the two hands. Person A and person B. Okay, so the two terminals are the two hands of A. The two terminals are the two hands of B. So if they're connected by both hands together, see, this is the hands of A, this is the hands of B, this is the hands of A. Sorry, this is the sorry. This is the hands of A, this is the hands of A. This is the hands of B, this is the hands of B. Then you see, if you were to use the two people analogy, they will also be holding both hands together. So hands of A, hands of A, hands of B, hands of B. See? So whenever they're in parallel, both terminals are connected. Whenever they're in series, only one terminal is connected. Okay, so now that we're clear with this analogy, let us take a look. Look at R1 and R2. Are they series or parallel? Let me give you 3 seconds to think. 1, 2, 3. The answer is they're in parallel. Why? Because you take a look at this. This is the hands of, you imagine, okay, I'm just gonna draw the person to make you imagine, okay? If R1 was a person, his hand is like this. And if R2 was another person, his hand will be like this. See? Both hands are holding together. So that means they are parallel. See, this is the hand of A. Sorry, this is the hand of R2. And also, this is the hand of R2. See, both nodes are holding together. Both terminals are connected together. So that means R1 is parallel to R2. Okay, so we're going to add up R1 and R2 together. So let us call this RA. Okay, so to find RA, we use the parallel formula. R1 is 100, R2 is 200. So this is 100, this is 200. So let me punch this in my calculator. Okay. So now I can redraw this circuit. I can redraw this circuit. So I shall remove R1 and R2, and then recombine them as RA. Okay? Then what else? So now you check any more relationships. So RA and R4, you see? They're connected in sequential manner like this and like this. So that means R4 and RA are in series. I think that's obvious, right? See, it just connected straight like this. They're only holding one hand together here and here, like that. This belongs to R4, this belongs to RA. So they are in series. So RA is in series with R4, so we can just add them together. So let me lump RA and R4 together. Let's call the sum of RA and R4 as RB. Okay, so RB. So RB is equal to RA plus R4, which is 66.7 plus R4 is what? 300. So 366.7. Okay. Yes. So now that we found RB, we can remove this and then redraw it as a single resistor like that called RB. So now it's obvious that RB is simply parallel to R3. If you're not convinced, let's use the hand analogy. This is the hand of R3. This is the other hand of R3. This is the hand of RB. This is the other hand of RB. So see, both hands are holding together. That means R3 and RB are parallel. So finally, we want to find R thevenin. R thevenin is the total resistance. So R thevenin is equal to 1 over RB plus 1 over R3. That means what's R3? 50. R thevenin can be calculated to be 44. Okay, so we've already done it. We found the thevenin equivalent. So now we just need to draw the thevenin equivalent. So the thevenin equivalent, as seen by the voltage source, can be drawn like this. Like this. The voltage source. And then sorry, if it's a voltage source, then it cannot be parallel. It will be in series, right, with the thevenin resistance, which is 44. And then the V thevenin here is, what do we find it to be? Forgot. 0.8. Yeah, so this is the thevenin equivalent, this diagram. Okay, so that's the end of this question.